Hello everyone, I am RCDT, Theory and Simulation lecture course. This is our next practical lecture. That is the one where I'm not standing in front of you at the whiteboard, but rather you are looking at my screen as I'm typing away the actual programs for simulations. And we'll be dealing today with solid-state NMR and EPR simulations. Now, a small disclaimer is in order. Done properly, these things should be using irreducible spherical tensors and Wigner functions. However, that's about 5 hours of just straight programming to implement it all from scratch. And because we have a policy here of never pulling any rabbits out of hats and programming everything from just the blank screen that you see is here in front of me, what I'll do is I'll implement a somewhat less general path, but the one that is compact enough to fit it into 1 hour lecture. So what I'll be doing is implementing rotations using sines, cosines and Euler angles rather than spherical tensors. The advantage, as you'll see, is a relatively straightforward notation, whereas if we did go ahead and use the full machinery of rotation group, this would have stretched for far too long, and that would perhaps be excessive. So there goes. There is just an empty MATLAB file in front of me, and we're just starting to code something solid state. So let's say we'd like to code an axial quadrupolar interaction powder pattern for nitrogen-14. Now, we'll proceed as usual. We'll introduce Pauli matrices, we'll build the operators, but before I start, we need to build the rotation infrastructure that would be turning our system around before we even start doing anything quantum mechanical. What I'll do is write a function that would take our 3x3 interaction tensor and rotate it by the angles that we specify. So, comments. Rotation function written by myself, function rotate interaction. Remember, we should be giving descriptive names to everything we write. This will be our interaction tensor that the function will take. And we'll be using Euler angles in this example, so let's say alpha, beta, gamma, and the function will return us a rotated interaction tensor. So, interaction tensor at the output. Okay, so let's just type in those rotation matrices, sines and cosines, we know them from school. Using extrinsic rotations for Euler angles, so what we first need to do is to rotate the system by gamma around the z-axis, then by beta around the x-axis, and then by alpha around the z-axis again. So R gamma, the rotation matrix around the z-axis by gamma, is going to be, the rotation is around the z-axis, and so it's in the xy plane, so we're effectively rotating x and y here. So what we've got is cosine gamma, then minus sine gamma, then 0, semicolon, sine gamma, cosine gamma, 0, and then 0, 0, 1. And that's our matrix. So what this does is it rotates things by an angle gamma in the xy plane, and it leaves the z-axis where it was. Now let's do the same for beta. So we've got R beta here. That would be a rotation around the x-axis, so the x-axis remains where it was. 1, 0, 0, it's not mixed with anything. Then here 0, then cosine beta, then minus sine beta, new line, 0 here as well, sine beta, cosine beta, of the matrix, just making it a bit prettier here. And finally the same rotation as gamma, but with the angle alpha, so we can just copy it from here, and that would be R alpha, which would have cosine alpha here, sine alpha, cosine alpha, and finally sine alpha. Okay, so these are the elementary rotations, and now we need to compose them. So the overall rotation R would in our case be first the rotation around gamma, then the rotation around beta, then the rotation around alpha, meaning R alpha times R beta times R gamma, because they are applied from the one that's closest to the vector to the one that's furthest away from the vector. And not forgetting some comments around here, so that would be gamma rotation in xy plane, that's beta rotation in yz plane, and this is alpha rotation in xy plane again. This way, when we come back a month later trying to figure out what's going on here, we will easily figure it out. And this is the total rotation. Now, as we know, when we rotate matrices, we have to apply rotation from either side. And so what we need to do in order to rotate our interaction tensor is the following. So interaction tensor would be R times interaction tensor times R transpose. And because we are dealing with orthogonal matrices, here the transpose is the same as inverse, but it's considerably cheaper than the inverse, so it's preferable in this case. And then just the end, we have finished the function, so apply rotation to the interaction. There we are, that's our function, and what this will do when we call it, you see MATLAB syntax checker has become green, no warnings, we've done everything correctly, is to rotate our interactions that we have supplied by those angles alpha, beta and gamma, and those angles we will be reading from the spherical averaging grid. Okay, let's save the file, save as, rotate interaction, and just create an empty file for the spin part of our problem, and we'll be calling that rotation function we've just written as necessary. So, comments, let's say it's going to be a quadruple powder pattern for nitrogen 14. So 14 and quadruple powder pattern, and function hello world with no input parameters. Now, because nitrogen 14 is a spin 1 particle, what we need to do is type in Pauli matrices in much the same way as we previously did, but they would be 3 by 3. So sigma x is equal to, that's just textbook data, you can pick it up in most introductory books, 0, 1, 0, 0, next line 1, 0, 1, and the last line 0, 1, 0, and very importantly divided by the root 2, otherwise they would not commute correctly. Right, that's our x Pauli matrix. The y Pauli matrix, sigma y, is very similar, but with a few sign changes and imaginary numbers. So 0 minus 1i, that's MATLAB's notation for the imaginary unit. 0, next line 1i, 0, minus 1i, and the last line is 0, 1i, 0, and also divided by square root 2. And finally sigma z is 1, 0, 0, 0, 0, 0, and 0, 0, minus 1. The three quantum numbers on the diagonal. Now, it's usually just for convenience reasons better to just keep them in one line. MATLAB parses the semicolon as the beginning of the next matrix line anyway, so we can just make it a little bit neater here by reordering the matrix somewhat, so it doesn't take up that much space. Like this. And of course, the thing that we need to check is that we've entered them correctly. It's quite a few things to type, and it's conceivable that I have made some mistake here. So what I'll do is just check the commutation relations. So if we did everything right, then sigma x times sigma y minus sigma y times sigma x should be exactly I sigma z, or alternatively, if we subtract 1i sigma z out of it, then the norm of the result should be 0. So why don't we print it and take a look? Okay, save this, entering the MATLAB window, just drag it into the area that's being recorded, and say hello world. And the result is not a 0, but it is 0 to what's called a machine precision. It's very close to machine epsilon, which is the smallest number that the double precision arithmetic can represent. We can actually take a look at what is the smallest number. It's thereabouts. In fact, identically the same. So we get epsilon 10 to the minus 16. So for all intents and purposes, the difference is indeed 0. So we have done it right. Okay, deleting this check. So what we now need to do is to decide what kind of quadrupolar interaction we are going to have, but let's write some comments first. So Pauli matrices for spin 1 particle. Curiously, the three Pauli matrices that I've typed here are generators of SU2. However, their powers, like sigma x squared, sigma y squared, and such like, that enveloping algebra, in fact generates SU3. And because we've got these squares in the quadrupolar interactions, in the context of magnetic resonance, the dynamical algebra of spin 1 is in fact the full SU3, not SU2, as is often the case in particle physics situations. Right, so let's just specify our interactions. Let's say Zeeman interaction. Well, we'll be working in the rotating frame anyway, so why don't we specify some offset? So omega Zeeman will be, let's say, 1000 Hertz. And we'll say that that's in Hertz. Just to remind ourselves, so that we don't forget to multiply it by 2 pi when we make our Hamiltonian. And then the quadrupolar interaction tensor, let's make it axial, and let's make it, say, 10 kilohertz axiality or thereabouts. So quad tensor would be minus 5000, 0, 0, then 0, minus 5000, 0, and finally 0, 0, 10,000. And you see this matrix is traceless. If we sum all the diagonal elements in here, the sum is 0. and it's axial because there is no difference between the x-x and the y-y component. And it's also diagonal because we can choose to treat our system, because it's such a simple system, essentially in its eigenframe. So if it wasn't diagonal, if it was rotated somehow, we can always say, well, why don't we choose our initial system orientation before we have done the whole powder average to be the one in which this tensor is diagonal. So, okay, we now have our Zeeman interaction, and we now have our quadrupole interaction tensor, which is a 3x3 matrix. So now let's proceed to make the Hamiltonian. So Hamiltonian, starting with a 3x3 zero matrix. So H is zeros 3x3, the same dimension as the Pauli matrices, and then adding the Zeeman interaction to it. H is H plus, not forgetting the 2 pi, because we always work with angular frequencies in quantum mechanics, then omega Zeeman times sigma z. And we can add it here because our Zeeman interaction is orientation independent, it just remains the same. However, our quadrupolar interaction is orientation dependent, and before we apply it and add it to the Hamiltonian, we need to decide which orientation it's in, and we need to rotate the matrix into that orientation. Which brings us to the point of choosing which orientations to select. There are various choices of spherical grids available, but what we'll do is just a grid that's uniform in two spherical angles in theta and phi. So let's say theta. Thetas, because there are many of them, would be a lin space, so linearly spaced array of numbers from 0 to pi, and let's say there will be 100 discretization points in theta. And then phi's will be lin space from 0 to 2 pi, and also 100 increments. Now, what's important in spherical coordinates is that we shouldn't forget the Jacobian. Remember, when we integrate functions in spherical coordinates, there was a sine theta, which reflects the fact that the point density is slightly greater at the poles of the sphere in this particular coordinate choice. So we should also add a vector called weights, and then assign those signs of thetas, and this would be element by element calculation of a sine for each angle theta, and we should apply these weights to the final calculation before we add them together, because that would assure us that the integration is correct. So we decided which grid to pick and which points and which weights. Now we need to loop over those points. So we set up a cycle for theta equals that lin space. So we'll be doing the calculation for each value of the theta in that 100 element vector in turn. And for each theta we need to loop over all the phi's. So for phi is lin space from 0 to 2 pi, and again 100 element vector. So it's a nested loop, and we've got 100 instances in the outer loop and 100 instances in the inner loop, so it will be 10,000 points. That is unfortunately the reality of such calculations. In very rare analytical or semi-analytical cases, powder averages can be done more efficiently, but in large time-dependent experiments with multiple pulses and various rotor-synchronized events, there is, unfortunately, at the moment, no way to perform this average except by powder. Well, to be very precise here, we are working here in Southampton on various ways to avoid grid integration in its entirety, but it will be a couple of years before these methods filter through to the mainstream. So for now, we are stuck with this grid. So for each theta, let us define a weight, because the weight is the same for each value of phi. So weight will be our sine theta, as we decided a few minutes ago. and then we are looping over the values of phi. And inside this inner loop, we are just repeating the same calculation with a different orientation. So I'll just make a little bit of space here and then close the loop, so that MATLAB stops complaining about the loop not being closed. Okay, so that's the nested loop over orientations, and what goes on here should be the simulation. Now, the first thing we need to do here is to rotate our quadrupolar tensor into the current orientation. So, rotate quad tensor into current orientation. And for that we will be using this function that we previously wrote, the rotate tensor. It would be convenient to just copy this into this function, and so Control V. So we'll call it current quad, where current refers to the current orientation. It will be rotate interaction quad tensor, the one that we've specified in here. And you see we've got three Euler angles in here, and we've got only two angles over a sphere. That is because our calculation is in fact insufficiently sophisticated to properly depend on the third Euler angle, and so we can get away with just two. So why don't we put alpha to 0, then beta becomes theta, and gamma becomes phi. And that will be what's called a two-angle average. So, okay, for each value of theta and each value of phi, our quadrupolar tensor will be rotated into that orientation, and the result will be called current quad. So what we now need to do is to add the corresponding quadrupolar interaction to the Hamiltonian. So create current orientation Hamiltonian. And we only need the secular part here, that is the diagonal part, so H is H plus current quad 3, 3, that is the Z part of it, times sigma Z squared, in brackets, just for the beauty of it, plus current quad 1, 1 times sigma x squared plus current quad 2, 2 times sigma y squared. Notice here that MATLAB actually multiplies a matrix by a matrix when you say square. If we wanted element by element square, it would have been dot power symbol. So just wrap it around a little bit here for convenience. And so another important thing is we shouldn't really overwrite it. So let's say H current here, so that our isotropic Hamiltonian is left untouched for the next iteration, that we've got the next instance of this loop over the angles. Right, so we now have our Hamiltonian, so the only thing that remains really is to run the simulation with that Hamiltonian and add the result to the total. So let's start with the density matrix on the x-axis in the transverse plane, as it would usually be after we gave it a pi-half pulse. So rho is sigma x, and just implement the standard time propagation infrastructure of the kind that we saw in the previous lecture, both derived at the board and programmed in at the console. So I'll just repeat all the steps, but I wouldn't particularly stop at them or explain them, because we already covered that material. So we need to choose the time step. In this case, the time step is probably best put to 1e minus 4, so about 100 microseconds, because the dynamics, because of this huge quadrupolar interaction, is going to be fairly fast. Then we build the propagator, p equals xpm, matrix exponential minus 1i times h current. times time step. So that's our step propagator. And then we just loop over the time step, and in this particular case we probably want about at least 20 milliseconds of a simulation. Let's make it 50 milliseconds. So we require about 500 steps. So 4 n equals 1 to 500. FID, the free induction decay, point number n, is going to be a trace of our observable state. Why don't we pick the observable state coil to be sigma x as well? I'll take it out of the loop in a moment. So a trace sigma x conjugate transpose times rho. So that's our observable scalar product. And then we propagate the density matrix forward. So rho is P conjugate transpose, which is the reverse propagator, times rho times P, and end of the loop. And we need to take a few things out of the loop here which don't need to be in there, and we need to pre-allocate a few things so that we don't increment the arrays in memory. In particular, the FID should actually be declared at this point, so pre-allocate the free induction decay, and FID would be zeros, 1 row and 500 columns. And here we will be not assigning but updating FID. N is FID n plus, and now we should remember that weight, that different values of theta should have different weights associated with them. So weight times trace sigma x times rho. So it will just keep adding to the FID at every orientation and at every time point. Now the propagator belongs here. Let's just comment around it. So compute the propagator. Then the time step clearly belongs outside. So I'll just copy it somewhere here. So timing parameters, that's our time step. Coil clearly belongs outside as well, it's the same everywhere. So here, timing and detection parameters, that will be our coil. And this shouldn't be sigma x, this should be coil, because we might change it afterwards. So this is time evolution. That rho, which is equal to sigma x, is the initial condition. And that is the current orientation Hamiltonian, and that's the current quadrupolar tensor. You see the code is now fairly neat. We might just add a few comments in here. So loop over phi. This one's obvious. It might not be actually even necessary. So compute grid weight, and then loop over theta. So if we come back to this code a month later, it will be perfectly clear to us what is going on here at every point. And if you open any source code file that is supplied as a part of Spinach, you would see this kind of commenting that makes the code quite readable. And it's important to do because other people will be using it, you yourself will be using it, you'll be modifying it. And it's really surprisingly difficult to get it even oneself after some time has passed. Okay, so let's just take a look through the code to make sure that we've done everything the way it is supposed to be. So we have our Hamiltonian. It's probably unnecessary here to pre-allocate it, we'll just assign it to the Zeeman interaction to start with. So we have our omega Zeeman, which goes into our orientation independent Hamiltonian. We've selected the time step and we've selected the coil states that we are detecting. We've pre-allocated our 5 100-point FID. We have computed a loop over thetas. We got the weights, we got the loop over phi. We have computed the current quadrupolar interaction, which is the rotation of the quadrupolar interaction into the current orientation. Then we took our orientation independent Hamiltonian and added the orientation dependent part to it that was coming from the current quad that's rotated, and it was the secular part of the quadrupolar interaction with those sigma xyz matrices which we've declared up here. Then we chose the initial condition for the propagation, that is the magnetization on X. We have computed the propagator under the current Hamiltonian, and we are running the time evolution for 500 steps. And at each individual step, when we are pushing the system forward, we are adding the free induction decay with the weight that corresponds to the current orientation to the total free induction decay that we in the end are computing. Now, notice that this is a fairly large calculation. The matrices are small, but we've got 10,000 points in space, and then we've got 500 points in time for each orientation. And in this particular case, it might compute reasonably fast, but it's always a good idea to run such things in parallel, and MATLAB thankfully supports that out of the box. We can just say par4, and in this case it says nope, it cannot do it because of the way our FID variable is used. There are too many nested loops in here. So in this case I think we should just backtrack. If we did reorder the loops in here, it could have been different, but it would take a considerable amount of refactoring in here to try and make that parallelization work. So we'll just leave it as it is and run it and see what happens. So plot FID, or rather the real part of it, because it will be complex potentially just due to the round of errors in the finite precision arithmetic. And well, let's see what happens. Now, in order to make it reasonably fast, I think I will initially at least have 10 points in theta and 10 points in phi before I run it, just in case. So clicking run and getting an encouraging looking oscillation. Now there's one thing that we need to worry about here, and that is the apodization. Of course, we haven't built in any relaxation theory, and so our signal doesn't decay. So we have to make it decay before we do the Fourier transform, otherwise the spectrum would not look smooth in the end. So we'll close this window and we'll just put in a little bit of apodization here. So apodization. And FID will be multiplied element by a decaying exponential of Lin space, so from 0 to 1 in the same number of steps as there are points in the FID, and we'll multiply it by -10 to make sure it decays. So it's just a standard decaying exponential function that we have multiplied our FID by. And we do the plotting again. Let's see what happens. Now we got a decaying FID, and that will Fourier transform good. Now for it to Fourier transform properly, we also need to make sure we've got quadrature detection, which means we probably need to update the coil state here. So it's not just sigma x, it's actually sigma x plus 1i sigma y, so that we are detecting the complex signal straight away. So when we save this, the real part shouldn't change, but the imaginary part would actually appear. There we are. And the final thing to do would be to Fourier transform it. So instead of plotting the real FID, we need to plot real FFT shift of FFT of the FID. And FFT shift in there is just to shift zero frequencies in the middle of the spectrum, as is conventional in magnetic resonance. So if we now click run, we should get the spectrum. It is rather unlikely to work on the first attempt, and so we're probably looking at some debugging pass before we get it to work. There we are. This certainly doesn't look like a quadrupolar spectrum to me, so we are looking at something that we haven't implemented or didn't implement quite right. The obvious thing is we are seeing the list of discrete peaks rather than a continuous powder pattern, so we're probably not making enough points in the angles, which is expected because I've reduced them. So let's take 50 points and theta and rerun and see what happens. Slightly better, but it's not a symmetric shape that I'm expecting, and so there's some kind of problem at the Hamiltonian level in here. So let's take a look at our Hamiltonian, what we've got in here. So we've got H current is H plus the secular part, and of course it's not the secular part that I've typed in here, it's the isotropic part, so we actually need to stick in the secular one. Right, so axiality of the interaction, so that would be current quad ZZ, so 3 minus a half times 1 plus 2, so current quad 1 plus current quad 2, so that's the amplitude, and times the secular part of the quadrupolar interaction Hamiltonian, which would be sigma z squared minus a half sigma x squared plus sigma y squared. So in a way we've got an axiality of the tensor times the same kind of axiality expressed in operators. So that's the secular part of that interaction, and let's see how that works now. Run. There we are. We have a nice symmetric picture in here, but we clearly don't have enough spherical integration points. You see, it starts painting itself more or less, but we still need a few more grid points to try and do that properly. Now, in our case, you would notice the interaction's actually axial. So when we are rotating it around phi, nothing changes, so I'll keep it to 1 point here, and I'll put 200 points for theta. Obviously, if the interaction was rhombic, we would have had the 5 points as well. Aha! Getting even better here, so you clearly see a nice quadrupolar pattern in this case, and I think if we take it to 500 points, the pattern would become smooth. There we are. That's our beautiful quadrupolar interaction powder pattern, of the kind that you would typically see in textbooks. Now, if we just kill the Zeeman offset to make it a little bit closer to the center, what we'll see is a classical textbook picture. There we are. Nice and pretty. And of course, if we add a little bit of rhombicity here, so if we put in not 5,000 here, but 4,000 here and 6,000 here, then we would have to integrate in phi as well. So if we make it back to 10 and 10, we'll see a somewhat undersampled, but still a powder pattern for the rhombic interaction. So if we get to 20 and 20 here, it will become slightly better defined. So you see more and more points. If we actually crank up the apodization, it will get a bit smoother as a result, so we'll need fewer spherical integration points to get that right. Typically such things are done on Lebedev grids. Our grid isn't particularly efficient, so if we get 40 by 40, maybe 40 by 10 phi is usually tolerating slightly weaker sampling. So see, getting even smoother. So 40 by 20 might take a bit longer. There we are, but well, in the interest of time, let's return back to the axial interaction here and only do the powder average with respect to one of the two angles, because we can get away with doing it and stick the apodization back to what it was. There we are, so nice and pretty powder pattern. So that's essentially it. You see, even here, even with this fairly simplistic calculation, we are running into the fact that spherical averages take a long time. Those of you who run easy spin, it is fairly unique in that it implements an analytical interpolated powder average that Stefan Stoll invented. But unfortunately, as soon as you start doing time-dependent experiments, even easy spin would revert to this explicit grid type calculation. But of course there are massive opportunities here for parallelization. We didn't order our loops carefully here, so MATLAB would not at least immediately do it for us. But the codes like Simpson, for example, do have intrinsic already built-in parallelization over MPI, and if you have a large cluster it will send individual calculations to individual cluster nodes. Okay, so we are done with the quadrupolar powder here, so let us save this. Let us foolproof it a little bit, so it will be, let's say, 200 by 200, so very large grid. It will run for a long time, but it will at least produce the correct results no matter what some future user would do it. And that's essentially it, so we'll just save this and move on to EPR. Let us simulate a simple nitroxide radical with an axial anisotropic G-tensor and an axial anisotropic hyperfine tensor that's collinear with it. So we'll change it here to say simple nitroxide simulation. We'll save the file as something else so that we don't lose the work that we've done so far. So say hello again world. We'll change the function name so that MATLAB stops complaining. Hello again world here. And let's just modify this file to have two particles now. One would be a spin half electron and the other is a spin 1 nucleus. So spin 1 Pauli matrices we have here already. So let's add the spin half matrices. Pauli matrices for spin 1 half particle. Similar way, so let's call this sigma 2x, sigma 2y, and sigma 2z, and copy them and replace them with spin half Pauli matrices for spin 1. We'll have electron as spin 1 and nucleus as spin 2. So sigma x we have 0, 1 half, then 1 half 0. This is no longer necessary. Sigma y, we have 1 over 2 here, then this 0 disappears, then this becomes over 2, and the rest of it goes, including the denominator. And the sigma z, we have 1 half 0, 0 minus 1 half, and the rest of it goes. Again, a cursory check. I'm just typing this out of memory just to make sure that we've done everything correctly here. So sigma 1x times sigma 1y minus sigma 1y times sigma 1x minus 1i times sigma 1z in the norm should be a small number. Norm, and let's just tell MATLAB to stop here. And we'll double check our Pauli matrices. So run, and let's take a look at what we've got. We've got the answer equals 0. So we've either defined them all correctly or defined them all self-consistently incorrectly. Both cases are fine because the Lie algebraic structure of it is observed. Right, on the interactions, our Zeeman interaction will now become anisotropic. That would correspond to the anisotropic G-tensor. So let's make it axial. I think I'll just drop the hertz here and the 2 pi here. We'll just specify them in angular frequencies straight away. In EPR, the interactions are considerably stronger than they are in NMR, and so we will increase the numbers appropriately. So let's say this will be 1 1e6 with a minus sign. That will be 1e6 with a minus sign again, and for it to be axial, so for it to have zero rambicity, this should be 2e6. So the x and the y components are equal. The z is minus twice the number, and we just shift the transmitter offset so that the rotating frame is precisely on resonance with respect to the isotropic part of the Zeeman frequency. So that would be Zeeman, and the quadrupolar coupling we'll replace with hyperfine coupling, so HFC tensor. And let's make it collinear with the Zeeman tensor, so that we don't need in this simple example to integrate them over two angles, just one angle would be sufficient. And I'll just make this equal to, say, 2e6, then 2e6, and then a minus here of 4e6. Now clearly, because the magnitudes of the interactions are now greater, we'll need eventually in the end to take longer time steps to make sure we digitize everything right, but we haven't got to that point yet, so let's save this and just proceed. Okay, our Hamiltonian contains the isotropic parts and the anisotropic parts. In this case, because we've specified it this way, the isotropic part is basically zero. It's all anisotropic, so we don't need to worry about this. Although, I guess let's add a little bit of isotropic hyperfine, just so that we've got something in the isotropic Hamiltonian, and also because there usually experimentally is some isotropic hyperfine present. So I'll just add the unit matrix, and I'll multiply it by, say, 1e6. So there will be a little bit of isotropic coupling present. And it's this isotropic part that we need to add to the Hamiltonian, and so we need to take a trace of it and then take 1/3 of that trace. So trace HFC tensor divided by 3, that would be the isotropic part of the hyperfine tensor, times the coupling operator in the isotropic case, so LX-SX plus LY-SY plus LZ-SZ. We will not pre-compute those operators now, we'll just put them together with crons straight away, and that's how this is done. So we need to take a Kronecker product or a cross product of sigma 1x with sigma 2x, then a cron of sigma 1y and sigma 2y, so add that here, and then the same for z, and all the line wrap and the brackets in all the cases. So we have y and y here, and z here, and that's the standard xx plus yy plus zz isotropic interaction operator. It would have corresponded to J coupling if we had it in NMR, and here it corresponds to the isotropic part of the hyperfine tensor. Right, so timing and detection parameters, we now need to change a few things. Here our typical interaction happens on the time scale of microseconds now, and so it's a good idea to put this to about 1e minus 8. We'll be observing the electron, and so we should take as coil the Kronecker product with the corresponding operators on the electron, cron with the unit operators on the nucleus, so that we only see the electron in our detection. So that would be cron. Then the electron is first, so we have sigma 1x, then a unit matrix for the nucleus, which is 3 by 3, so I3. That would be our x, and to just enable the same kind of quadrature detection that we had here for the NMR case, I'll add the y component here as well. So we'll be detecting on the L plus operator, which philosophically speaking isn't strictly Hermitian, and so it's not a physical observable as defined in the philosophy textbook, but we are not philosophers, so we don't care, and so we just put an operator with complex observables and not worry about the deep existential implications of that. It's the same pulse-acquire experiment, so we are not doing a slow passage EPR spectroscopy, we are doing a pulsed EPR spectroscopy experiment here. So we'll just have the same FID, it will have 500 points in it, except the point spacing in our case will be considerably shorter because we are dealing with much faster dynamics in this case. And well, the same loop over theta, the same 200 points, the same weights. I've chosen these things rather carefully that they are axial and collinear, and so we wouldn't have to actually take a loop over phi. So I'll just put 1 point in here so as to not waste any time. And now what we need to do is to rotate our tensors into the current orientation that is specified by those theta and phi angles. And now that we've got two anisotropic tensors, we've got this omega Zeeman and we've got the HFC tensor, we need to rotate them both. And importantly, in the case of HFC tensor, we need to first get rid of the isotropic component because we have already added it here at this stage. So after I've added it here, maybe inside the loop actually, it doesn't particularly matter, the mathematics here is pretty fast. But just for the sake of, I guess, programming accuracy and neatness, we'll just destroy the isotropic component here so that we don't drag it along. So destroy the isotropic part of the HFC tensor. No longer needed. So we'll take our HFC tensor and say that it's equal to the HFC tensor minus the part of it that is isotropic, so I 3 times that 1/3 of the trace, so trace HFC tensor divided by 3. And that will simply just subtract the isotropic part and only leave the anisotropy that we're actually interested in. Okay, so let's now rotate this thing. So we'll just copy this line twice and we say rotate interaction tensors into the current orientation, and our current HFC will be rotate interaction HFC tensor by the angle theta and phi. So that's our HFC tensor, we have rotated it, and current Zeeman will similarly be Zeeman tensor that has been rotated by theta and phi. So we've rotated this and we've rotated this. I should perhaps rename this into Zeeman tensor just to make it all uniform. Tensor. You see MATLAB's highlighting things that I may have missed, and it's quite convenient because really it is possible these days with this online syntax checking to just write the code and have it run on the first try. You may have noticed we did rather little actual debugging. Even in the previous example, all the debugging we ever did was physical rather than programming. That's because MATLAB these days essentially just enforces the correct syntax and starts complaining really loudly. This thing goes red and various warnings pop up if we start coding something that the syntax checker knows is not likely to run. Right, so okay, so we've rotated this, we've rotated this, and now we just need to assemble our Hamiltonian at the current orientation. And the things that we need to do are very similar. Because we are working at high field, we need to just stick in the secular parts of these tensors that we've just rotated. The secular part of Zeeman interaction is just the LZ, and the secular part of the hyperfine interaction is the same crocodile as this, except that there will be Kronecker products in here rather than just the powers that we had for the quadrupole tensor. So let's do the necessary editing and see what comes out. So in the case of the Zeeman interaction, we have it on the electron, so we need the electron LZ operator with the corresponding amplitude. So it will be current Zeeman 33 times cron the LZ operator on the electron cross the unit operator on the nucleus, so sigma 1Z cron I3. And that's our Zeeman interaction, and what we now need to do is to add the hyperfine interaction to it, and we'll need to edit this in a very similar way to what we previously had. It will be current HFC 33 minus a half current HFC 11 and then current HFC 22, and these sigma z's, which were just squares, they will be sigma z1 times sigma z2, so we need to just stick those crons into here. So cron sigma 1z sigma 2z, that is the zz component of it, and then here we've got cron xx and cron yy in the same fashion, so I'll just copy paste it into here. So x and x, and then in this case we've got y and y, and just making sure that we've got enough brackets in here. Yes, we do, and that should just run. Okay, so that was the Hamiltonian. Now our initial condition, since we are observing the electron at room temperature presumably, so we just have the X magnetization on the electron and the unit operator on the nucleus. So we've got cron sigma 1x I3, that would be the X magnetization of the electron, and the rest is basically the same. We've got our propagator, which is the matrix exponential of the current Hamiltonian. We have our time evolution, that is for 500 steps, and the FID at the point n is FID at the point n plus weight and the observable of our coil and our row, and it propagates forward. And you see, this is the beauty of MATLAB in then when you see that when you tell it to add two matrices, it doesn't matter what the dimensions are, it all adapts. The old timers amongst you may remember the old Fortran nightmares where everything had to be declared explicitly and loops had to be taken in a much more down to the metal way. MATLAB really abstracts and removes the necessity of doing that from the user. We would have had to call some really horrible libraries to compute Kronecker products if we did it in any low-level programming language. Hence my insistence on using these things like MATLAB and Mathematica, because they really emphasize science rather than bare metal grinding kind of programming that people used to do in the early years. Your time is really much better spent programming in high-level languages and just using a bigger computer really, rather than worrying about the efficiency of every line of the code, as was the case just 10 years ago, because the computers were not fast enough. So it's a bit of a blasphemy here that I'm preaching, but do focus on science. If you need a bigger computer, we're gonna buy you a bigger computer, but it's important to get scientific results out of it. Right, so and we've got the apodization and we've got the plotting, so if we just run this, it should actually run. Now I've guessed the time step, so we might be out of the correct bandwidth in the detection a little bit, but let's just run it and see what happens. I'll also drop this maybe to 100 points just in case to make sure that it doesn't take too long. So run. Okay, we clearly overestimated the bandwidth. We've got something in the middle, but it has a width, but the bandwidth is clearly far too great. So why don't we choose the time step to be not 1e8 but 5e8, so 50 nanoseconds in this case, and rerun. See, it's getting somewhere, so we're starting to see this characteristic shoulder in here, but the rest of it is obscure, so why don't we get it a little bit closer? So I'll call it 1e7 in here, and let's run it. So yep, getting better, and you see we've got the fairly smooth variation in various places, but we also have these jagged edges which are simply telling us that we are not taking enough points on the spherical grid. So I'll go back to 200 points here, and I will also take a slightly longer time step in this case. Right, so we're getting something that looks like a nice EPR spectrum. Remember that we'll need eventually to take a derivative of this to match what there is in the experiment. And maybe I should just make it 400 points rather than 200 points in the theta average, and then we'll probably get a pretty picture. Right, there's the pretty picture. And you see, it's rather difficult to say whether, in this case, we've done it right. It's an obscure pattern, it's got multiple splittings, and it's a powder average, and so it's rather hard to tell whether this actually corresponds to the physical system that we've got. In that case, the debugging of it and the testing would typically proceed through considering various special cases. In this particular case, a really simple such thing would be to put the hyperfine tensor to 0. In which case what would happen is we will have a pure Zeeman tensor, which will be just an axial shielding picture, which we all know from textbooks. So why don't we put the anisotropic part of the hyperfine tensor to 0 and see whether it simplifies anything in our picture. Note that I've still left this in. We'll zero it in a moment. So here's our picture, became considerably simpler, but still it's split into 3 as the hyperfine coupling should do if it's isotropic, so we clearly are getting something right somewhere, and probably let's just put this to 0 as well and see the pure G-tensor anisotropy pattern in the result. That looks very characteristic, and it will immediately tell us whether we've got it right or not. So that's the calculation. There we are. And yes, those of you who did solid-state NMR spectroscopy will instantly recognize the CSA. And because EPR and NMR spectroscopy are essentially mathematically isomorphous, it doesn't really matter which one it is. You would notice we never actually said here what the identity of the particles is. We just said spin 1 and spin half. This could be electron, this could be the nucleus, this could be 2 nuclei, this could even be 2 electrons, one belonging to some high-speed nucleus and interacting with some anisotropic dipolar interaction. So because the mathematics really only depends on the number of energy levels in the particle, it doesn't particularly matter, and so in this instance we can actually use our NMR knowledge of what a CSA looks like to judge the EPR spectrum. Okay, so it does look, certainly from the looks of this, that we got it right. Typically for production calculations what would be necessary is we'd need to make a few other checks and balances. In particular, I'm skipping here the various factors that go into the Hamiltonian here in the irreducible spherical tensors. There are a few normalization things that should be added here, but because we are really not stating what is on our x-axis in here anyway, it would just be an overall scalar. So a production grade calculation would need to do some fairly meticulous checking just to make sure we haven't lost a factor of 2 or a factor of pi in various places, but basically the general scheme of things in here, as we can instantly tell from this special case, is correct. So let's put back the hyperfine coupling and recalculate the spectrum. So there's our pretty picture, and the last thing that we need to do in this case is to notice that EPR spectroscopists, for various historical reasons, it was to do with noise cancellation and sensitivity, usually record the first derivative of the spectrum rather than the spectrum, and thankfully MATLAB just has a simple finite difference differentiation routine. Again, there are better ways of differentiating a spectrum. We could have used spectral differentiation, we could have used Chebyshev differentiation. Spinach, for example, implements various multiple point finite difference stencils that are adaptive and make sure that they all remain accurate in a variety of circumstances. But for our purposes here, really the only thing that we need to do is to just diff it. And diff tells MATLAB to compute a finite difference derivative and just plot that derivative instead of the actual function. And there we are. That's the derivative, and that's just the look of a fairly typical, well-resolved and differentiated EPR spectrum in a solid state in its derivative representation. Okay, that's it, and let's just run through what we did. I quite deliberately didn't use standard software here. In principle, it is of course possible to just go to our website, download Spinach, type all these interactions into the proper example set file, press enter, and instantly the picture would appear and you'd know that it's correct. That would perhaps take you past the PhD, but not much further. Really, it is fairly essential at the time that you are doing scientific development beyond running the standard experiments and standard theoretical calculations into the unknown. It is of extreme importance to actually understand what's going on behind the bonnet of the various software packages. And here we just took an empty page of MATLAB, and in front of you I've built from bare scratch all this simulation, and you can see that we are getting textbook results for textbook systems with not too much effort. I think the lecture length was just about an hour, so it's not that hard to program these things. So what we did was to define the Pauli matrices for the spins. We have defined the interactions, we have defined the isotropic Hamiltonian, which doesn't depend on the rotation. Then we did specify the timing parameters and the detection parameters. We no longer want the isotropic part, it's already in the Hamiltonian, we are only rotating the anisotropies. We are looping here over two sets of angles. Now, because I've constructed the system carefully, we only really need theta. In systems where we have rhombicity or we have multiple axial interactions at different orientations, we would have had to also loop over the phi angle. That would have taken considerably longer. And in really sophisticated simulations with rotor-synchronized sequences in NMR spectroscopy, it's actually necessary to average over all three Euler angles, and that really takes an awful lot of time. So in this simple example, we've constructed the system that is not requiring that. We just do at every instance of the grid our rotations. We rotate the interactions into that frame, we construct the Hamiltonian, and then we just carry forward the usual pulse acquire simulation with a matrix exponential for the propagator, pushing the feed through just the evolving system in time, and recording it and adding it with the right weight to the total. Then just running the apodization to make sure we don't have any wiggles on the Fourier transform as the real instrument would. It's either a simple model of relaxation or just a digital signal processing technique. You can look at it either way, and then we just plot it, and that is the result of it. Okay, that's the end of the lecture, and I'll see you next week.